You tell me when can I start?
Yes, please go on. You can start, I think.
Okay. Hi everyone. I am Rafael Ek. I am from Mexico, and I'm gonna present this poster called Optical Fiber Taper Simulation and Manufacture from standard to micro size. This is I'm gonna show you the mode field intensity evolution that we made. We start with a single mode fiber from Corning glass, and we design the shape of the fiber, and we divide it in several points just to evaluate to find the fundamental mode in this with this diameter. As we see in this graph, we divide it in three sections in order to use different equation. In the first section, we use weak guiding approximation. In the second section, when the fibers start to be thinner, we use Monnerie equation, or it means that we have three different refractive indices. And in the last part, in the last section, we use exact modes. This is because we use really thin diameters. So this is the shape, and this is the mode intensity evolution of the fiber. Also, we simulate the spot size, the central peak intensity, and also we check if it's adiabatic or tapers, or this simulation. This is the experimental design that we are using for pull the fiber. And we use a laser on 13 nanometers. In order to heat the fiber, we use a microceramic heater and two pulling stations just to pull the fiber. And in the other side, we use a photodiode in order to measure the power losses during the process. As you see, I show you here the picture of the microceramic heater. Is around 25 millimeters by 25 millimeters. So it's small and have a small thing to put the fiber as around 2 millimeters. In this part, we put the fiber. So this micro heater, we can reach temperatures around 1500 degrees. So another thing, we're studying if our tapers are adiabatic or not. So we use this equation. When means that we have two limits. The left part of the equation is for the modes, mixed mode that we have into the fiber. So we use the radius along the taper and the constant propagations. And in the other side, we use the also the radius with also the constant propagation. And I show you here two graphs that we simulate. In the first one, you can see that the limit slope is not too higher than the taper slope, so means that the taper is not adiabatic. And in the second graph, we can see how if we have longer taper, we can have adiabatical tapers. So if we want really nice tapers with according with the adiabatic criterion, we need to have a long tapering. So our first result that we have, I'm going to present in this part. This, for example, this one, we measure in the scanning microscope, electron microscope, and we can see that we can reach tapers with 800 nanometers. And in the left graph, I show you the shape of the taper. That if you see, is almost the same that we have in the simulation that we have in the first graph. But also we measure the losses during the process, as I show you in this graph, and we have losses around 0.56 dBs, means that our taper is not completely adiabatic, and we can prove that with this graph because also we found the propagation constant, and we use the adiabatic equation, and we saw that also the limit slope is not too high than taper slope, so means that also is not adiabatic taper. Another result that we have, for example, if we pull a little bit more the taper, we can see that we can reach also less than 1 micron of diameter, but the power losses is too high, so means that this tapering is not good for certain applications. We have another results that I couldn't put in this poster, but also we reach diameters around 200 nanometers and long tapers around 6 centimeters of long longer, and means that we have adiabatic tapering. Also, we can prove with the equations. So now we are trying to measure the diameters of the taper without break the fiber. For example, I show you here that when we go to the SEM, is completely it's a challenge to manage this kind of diameters because it's too thin. But we can conclude that the optimal fiber external diameter values for the smallest spot size and largest mode field intensities were found, and a reduction in outer diameter size around 800 nanometer still guide the fundamental mode with an expanded evanescent field was obtained. So thank you so much. If you have a question.
Thank you, Rafael. Anybody has some questions, please? Maybe I have a question. I see your pulling time is quite short. It is only 20 seconds. In our experiments with flame, we pull taper maybe 3 minutes in total time. And it's nice to see that it's also possible to pull faster, and it does not influence the surface quality. Can you comment on pulling time?
No, also here the pulling time, we change different parameters in order to pull the fiber and obtain different diameters. And here also is 3 minutes the pulling in time. I mean.
It is 3 minutes, yeah?
Yeah.
Okay. Yeah, thank you.